This is part 2 in a series of videos in which I'm attempting to repair an Olympia ESW 100-KSR. It's basically a typewriter with a serial interface and was often used as a computer terminal. And quite an interesting machine. It's a lot newer than most equipment I work on, but it still has some very interesting features. Now, in the previous video we had a look at this, and there was a lot of damage on the board due to the batteries having leaked. And as ever, for some bizarre reason, the designers put the batteries at the top of the board, so all the acid leaked down onto some components, including the power connector. And although you probably can't see them, I've replaced some ceramic capacitors that were on the underside or underneath the connector. They'd been completely eaten away. All that was left of them were the leads. And I replaced those. I replaced the missing transistor. As you can see, I popped the batteries out of the board. They put up a bit of a fight. The board was fairly badly corroded and damaged, but I've cleaned it up. It's come up fairly nicely, and it's all the tracks luckily are intact. There doesn't appear to be anything that's missing off there now. The connector will need replacing. It's in a very poor state. All the pins are fairly badly corroded, but they are at least now making contact. However, the unit's still not working. We still have the same fault. It's a noise alert. I'm just going to turn it on. So it's still doing the same thing it was. Now, the current consumption has actually risen, so something's changed, but nothing significant. It's not working. And the next thing we're going to do is check the voltages coming out of the supply. There is also a 12-volt regulator on the this is the microcontroller board. I suspect, I'm a bit concerned that these microcontrollers may have failed. They are quite susceptible to damage if there's an issue with the power supply. But what we'll do now is measure the voltages. The 12-volt regulator on the controller board is a local regulator to provide the 12 volts for the devices on this board. But we'll get the voltmeter in. I will probably disconnect the sounder at some point to stop it being so annoying, but at the moment it is going to come on when I power this up, unfortunately. I have put some foam over the top, but it's still a very loud sounder, so unfortunately it will be a bit annoying. What I'm going to do is measure everything with reference to ground, which is this track here. We should have 5, the 2 blue leads are both ground. These come from the power supply, and we should have 5 volts, 35 volts and 9 volts. So we'll check that, see what we actually have. Okay, so as you can see, the 5 volts is present. The 35 volts was showing as 8.5 volts. I suspect that is leakage through the driver devices, so I suspect there's nothing at all on the 35 volts. We'll unplug this in a minute and check. And we had 9 volts on the 9 volt rail. Now, the only voltage high enough there, of course, to feed the 12 volt regulator is the 35 volts. So I'm just going to check to see if there is any 12 volts coming out of that regulator. That's this device up here. We'll just see if there's anything over there, and chances are that that 12 volts is completely absent. Okay, so as you saw, we're getting 5.3 volts on the input. Again, I suspect that's just leakage, and I don't think there's anything coming directly out of the regulator. What I'm going to do is just check to see if this is indeed connected to the 35 volt rail. So we'll come from the 35 volts. I notice there's this big power resistor. You probably can't see it again. There's a big power resistor next to the regulator. So I think that's just like a dropper for the regulator, so there's no heatsink needed. So I suspect we are connected to that point, which we are. So that's being fed from 35 volts, hence why there's no 12 volts output on this board. I'm going to unplug this connector now. Luckily it will stop the sounder, and we'll see what voltages we're getting direct from the power supply. I suspect there's going to be nothing at all on the 35 volt rail. So we'll power it up. Now there is a big clue as to the type of power supply, by the way. I'm not sure if you can hear it. A very loud hum, so we'll come back to that later. Okay, so we'll measure this. These are both ground. Okay, so 5 volts. That's fine. Should have 35 volts here, and there's nothing, and then 9 volts on this one. A bit high at the moment, but that looks fine, but no 35 volts. So I suspect what's happened is the fuse in the power supply has blown. If I move this connector out of the way, these ceramic capacitors here are the ones that I replaced, but all that was there before were just the leads from the original capacitors, and these are kind of arranged crossover, and there's normally the ceramic disc in between them. But when the disc disappears, these two leads short out and it blows the fuse. So I suspect that's what's happened. So what I'm going to do is get this board out of the way, and we'll turn our attention to the power supply. Now, before I do that, what we'll do is have a quick look at the schematic. Okay, now I don't have the schematic for this particular machine. I don't have any manuals, but this is a schematic of a very similar machine, and manufacturers tended to stick to fairly standard formats at particular periods in development. So this is the schematic of a similar machine. You might want to just pause the video at this point and just try and figure out what's going on here. It is quite interesting. Looks very simple, very basic, simple, straightforward supply, but there's something very special about this supply. And if we look at the input, it says 220 volts 50 Hz, 115 volts 60 Hz. It's not a switching supply. There are no taps on the transformer. Ignore this, this is just a filter. So how can we have this range of inputs without any taps on the transformer? And if we look across, we've got some fairly specific outputs here. The 5 volt rail has got a regulator, but the others don't, and yet they have fairly specific output voltages. Now, of course, I'm cheating here. This is not the entire diagram for this supply. If I get the full diagram, hopefully things will become clearer, and with this addition at the bottom, hopefully this explains what's going on here. It is, of course, a ferroresonant transformer, and if you're not familiar with those, I posted a series on them a while back. You may want to go and have a look at that to understand how these transformers work. The clue I mentioned earlier was the loud buzz we were getting from the power supply. It's usually a bit of a giveaway that it uses this type of transformer. They do tend to emit quite a lot of noise. So what I need to do now is get access to the power supply. So I'll get this board out of the way. We'll have a look. Hopefully it's just a blown fuse, and we can get to some fuses without taking the entire power supply out. Okay, I've loosened the 4 screws that hold the main print mechanism to the chassis, so this whole thing is now sitting loose in the case, so I can now take these parts out. Before I remove the keyboard, I need to remove this linkage, this mechanical linkage that runs to the back, but it goes underneath the print mechanism. Now if you try and take it out, you can remove it with this in place, but there's a danger you're going to break the little plastic tab off this power switch. So it's better to remove the spring clip off the outside. So I'll just get it out of the way. And then once that's removed, you can just slide the power switch off this shaft and get it out of the way. And that way you're not going to break this tab off. Otherwise what happens is this will snap off, and you've got a bigger problem to deal with. So once that's disconnected, you should be able to lift the keyboard out. It just sits in a couple of little spring clips. Okay, so we can get this out of the way. And with the keyboard out of the way, we can now do the same thing with the entire print mechanism. It will just lift up and out. I'll have to move the camera out of the way to do this. This is fairly heavy and I don't want to damage anything. So I'll get this lifted out, we'll get back on camera and have a look at the power supply. Okay, I've got the print mechanism out of the chassis. Now in theory you can get the power supply out of this without taking the entire mechanism out, but it's just far easier to do it like this. You're less likely to do any damage. Just be careful with the power switch. You've got this power switch down here that connects to that link that we removed, and make sure it gets reconnected when you put this back in. But it's easier doing it like this. You're far less likely to do any harm. And also, if we disconnect this is kind of a socket for the power connector, and it should come off, and that just disconnects. And we should now be able to move the entire supply to the left, and it should then pop out. It can be quite tight, so we'll give it a go and see if it will actually move. Okay, that didn't come out too badly. The little release tab was stuck on the back. Once I'd released that, it popped out fairly easily. As I say, you can get this out without dismantling the entire machine, but I wanted to dismantle the machine to have a good look at the print mechanism anyway. Okay, so what we can do now is have a look, see if any of the fuses are blown, check the rest of the parts. You can see it's a very simple power supply. I'll get the printer out of the way and we'll turn our attention to this. Okay, so we've got a power supply, and we'll start off by checking the fuses. So we've got a couple of fuses here. Get our test meter in. I've got it set to continuity mode, and we'll test the fuses. Okay, that one's blown, and that one's fine. So let's just get the one that we think is blown out. And that is indeed open. So looking at the fuse, 1.6 amps, 1.6 amps, that's correct. I'll get a replacement fuse, we'll fit that, power this up and see if our rails return. I fitted a replacement fuse, so now both fuses are intact. I've done a quick check with all the caps and I can't find any that are short, so it should be fairly safe to power this up. I do of course need to refit our interface. So we've got this, all this is, it's just a connector, weird connector they made up to connect the standard input socket to this through the remote power switch. So that just plugs onto this, just clips into place. We can now connect this to our main supply. Notice there is no earth pin on this, hasn't broken off, it just wasn't ever earthed. And what we can now do is power this back up and see if we have our 35-volt rail back. I'm going to try and connect this before I power it up so we can get a fairly quick read. Not quite sure if the switch is in the on or off position, so we'll power this up. It's in the on position, and we do now have our 35-volt railbacks, showing 38, but and it's dropping quite quickly, so I'm going to turn that off. As you can see, I've taken the power supply apart, and what I actually found was it wasn't the capacitor, the bridge rectifier had started to fail. So I've replaced that. We'll run it back up. As I said, this is a ferroresonant transformer, and if you've seen my series on these, they're quite fascinating. You can actually see the magnetic shunt, that's the bit just sticking out here, that is a short circuit for the flux in the core. And if you're not familiar with these, I'll just quickly demonstrate this. So although we have a circuit that is pretty much identical to this, there's no regulator in here, and we're going to run this up from 0 to 240 volts, and we'll be looking at this point here with the multimeter. So we're looking at the output, so it's just rectified and smoothed. There's no regulation here whatsoever in terms of electronic regulation. It's all down to the ferroresonant transformer characteristics. So we turn the power on, we're at 0 volts. We'll start to increase the voltage. Notice the voltage rises very quickly. So we're now at about 50 volts AC going in, and we've got 26 volts coming out. We'll keep going up. And this rail is about 38 volts unloaded. So as you can see, the voltage is still rising. And we're now at about 125 volts. And we've reached our 38 volt target. But if we keep going up, you'd expect with a normal transformer, if we double the input voltage, we'd end up with over 70 volts coming out of this. But that's not what will happen with this transformer. If I keep going up, the regulation characteristics of the transformer kick in, so we're now approaching 200 volts. We're at 240 volts, and we're still 38 volts coming out of the transformer. So that's the advantage of ferroresonant transformers. They have a self-regulation characteristic, and it really simplifies the design of the electronics in a power supply. They do have some drawbacks, but as I say, if you go and look at the series I posted on them, it is quite a fascinating type of device. So this now seems to be working. What I'm going to do is leave it running for 3 or 4 hours loaded. I'll put a few loads on this just to give it something to do, and assuming it survives, then I'll reassemble this. We'll get it fitted back into the typewriter and see if we've made any progress. I left this running for nearly 4.5 hours, and it just seems to be fine. It's not even getting particularly warm. It's kind of warm to touch, but it's certainly not hot. None of the capacitors are getting hot, so they're all fine. The regulator doesn't have a heatsink on. It's a really weird mechanical assembly on this power supply, so all I did was just temporarily clip a heatsink onto that. But other than that, it seems fine. So what I'm going to do now is switch it off, reassemble the power supply. We'll get it refitted to the printer's chassis and see if it starts to come to life. I suspect it won't. I've got a feeling that this may have damaged the MOS devices. They're very susceptible to damage when the power supplies start playing up. But fingers crossed, we'll see some life in the machine. Okay, I've got the machine reassembled, and what we'll do is power it back up and see if we've made any progress. I'm not holding out a lot of hope that it's going to run. I strongly suspect we've got an issue with the MOS processor, but we'll give it a run. With any luck it will start up, but let's see what happens. So again, noise alert. We are going to get some noise from the sounder if it doesn't start up properly. I'm not actually sure what it would do if it does start up properly. The one I worked on previously of this model just beeped once when I powered it up, but obviously it depends on what the firmware is that's fitted. Okay, so we'll power it up, and as expected we're getting the tone again. Current consumption has risen. It's quite a lot higher than it was, so we'll test our rails, see if they're all present now. So 5 volts, a 35 volt rail is there, and so is the 9 volt. And finally I'll just check the 12 volts on the processor board, which is now present as well. Okay, so all our supplies are intact. They're within the range we would expect to see them. So it looks like we have a problem with the processor not running. So that's what we'll look at in the next video. It could be something simple like it's been held in reset. It could be something much more complex. It may even be that the processor or one of its support chips has failed. I have already popped the ROMs out and read them, so I've got copies of the firmware, and they both seem to be working fine, so it's not a problem with the ROMs. They are fairly robust. They're 2716s, they're fairly robust. but the MOS processor and its support devices are extremely fragile, and quite often they do fail. So that's what we'll look at in the next video. We're a bit closer, at least we've got some power now, and we've got rid of the corrosion that was on the board, and so hopefully in the next video we can make some progress.